Antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium.
Welcome to Nate, Jack, and Christian's Dummy's Guide for Resonance Structures. We have quite the hot topic today, something that has messed up students for quite some time: resonance structures. Resonance structures are when you can't describe a structure with a single Lewis structure. What we can do is use multiple Lewis structures to describe a single compound. Let's look at an example.
Zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold protectin.
Now let's look at an example. This compound is nitromethane. If we draw the typical Lewis structure, it looks something like this.
And iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium.
Looking at this Lewis structure, we see that there's a double bond on the oxygen and a single bond on this oxygen. But since they have similar electronegativities, they're going to be pulling the electrons at an equal rate. So, looking at this molecule, you can see that although we have the double bond on this oxygen, it's also the electrons in this double bond are going to be pulled by this oxygen as well. Therefore, we have to denote that there is another Lewis structure that's possible for this molecule.
And boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium.
This compound is the same as this Lewis structure. The only difference is that the double bond is on this oxygen as opposed to this oxygen. Now let's take a minute and figure out what this means. We have one structure that shows the double bond on this oxygen, another structure with the double bond on this oxygen. The actual compound is a hybrid of both of these structures. The electrons are being shared by both oxygens at an equal rate. Sometimes it's easier to look at it with another type of notation. We can draw this nitromethane with this kind of structure. This notation helps us really visualize that the electrons are being shared both of these oxygens, rather than just how one Lewis structure.
And erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercurium, molybdenum, magnesium, dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, plutonium, palladium, promethium, potassium.
Let's try to look at some analogies to help explain resonance structures. Imagine you need to describe a nectarine to a friend. You respond by telling your friend to imagine a peach and a plum in their mind. A nectarine has characteristics of both a peach and a plum. It tastes like a peach, but the outside is nice and smooth like a plum. Now, a resonance structure is just like the nectarine. To imagine the nectarine in your mind, you combine both of these delicious fruits, the plum and the peach, into a hybrid of the two, which is the nectarine. In case you aren't a fan of the delicious taste of nectarines, let's try another analogy.
Polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium.
Let's say you're driving up to your uncle's farm for the summer, and he just purchased a mule from the state fair. Quite a nice one, too. Looking at the mule, you notice that it is a combination of both a horse and a donkey. Now, the mule is not at 1 second a horse and the other second a donkey. Rather, it is a hybrid of both of them. Now, a resonance structure is like the mule. It is the hybrid of a horse and a donkey, just like the resonance structure is a hybrid of the two fictitious structures.
Chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium.
In case mules aren't your fancy, how about another analogy? Let's imagine you have two cans of paint, one red and one blue. When you mix these two cans of paint, when you look into the can, you do not see red or blue paint, but rather a mixture of them. This is like a resonance hybrid. The mixture is in fact purple. In a resonance structure, you only observe the hybrid of both of them, rather than the individual fictitious structures. Note one more time that this is not an interconversion or a reaction, rather a one single mixed compound.
And chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard.
Now let's look at some examples to reinforce these ideas. Take a typical benzene ring. Benzene is composed of a 6-carbon cyclic structure that contains conjugated double bonds in a typical Lewis structure. The same compound can be drawn this way. Based on one of these Lewis structures, you would expect that the carbon-carbon bond lengths to be approximately 133 picometers for double bonds and 154 picometers for single bonds. However, what is experimentally measured is that every carbon-carbon bond has a bond length of exactly 140 picometers. How can we possibly explain this? Resonance. As a hybrid, we actually observe this structure. We can solve a typical resonance problem by using arrow push. Let's break it down. By using arrow push, you can see how we get from one Lewis structure to the other.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and
Resonance structures have applications throughout much of organic chemistry. Let's look at one of the most important applications, acidity. When evaluating the strengths of acids, it is always important to look at the stability of the conjugate base of the acid. Whichever conjugate base is more stable will correlate to the stronger acid. Let's look at a specific example. Let's compare the acidity of ethanol, acetic acid, and isopropyl alcohol.
americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine.
While all these structures are similar, their acidities are very different. Let's take a look at some of the data. The pKa of acetic acid is 4.5. The pKa of ethanol is 16. And the pKa of isopropyl alcohol is 16.5. Now the reason that acetic acid's pKa is so much lower than these two are because of the resonance stabilization of the conjugate base. Let's draw the conjugate bases of all these molecules.
And thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium.
These two molecules have lone negative charges that can't be stabilized within the molecule. But acetic acid is adjacent to a double bond which can stabilize the negative charge. Using our arrow push notation, we can see that the electrons can drift towards the other side of the molecule, thus stabilizing the conjugate base. One more time, we can see that the electrons are more evenly distributed through the molecule, and therefore it's going to be a lot stronger than the corresponding similar structures.